Let's take a look at the probabilities associated with moving from one state to another after a certain number of trials. For example, let's say you had a situation that looks something like this. We had two states, state A and state B, and there was a 30% chance of staying in state A and a 70% chance of leaving state A. Then for state B, let's say there is a 60% chance of staying and a 40% chance of leaving. So that would give us a transition matrix. I'm going to call it T. So A, B, A, and B. From A to stay in A, 30%. To go from A to B is 70%. To go from B to A is 40%. And to stay in B is 60%, so to go from B to B. Notice that as I add my rows up, they all equal 100, or 1, and it should be 100%. There shouldn't be anything outside of there. So if this is 0.4 and this is 0.7, we did something wrong. Now watch what happens. What if we wanted to know what is the probability of starting in state A and moving to state B in 2 trials or 2 cycles, okay? Let's say that was the question we were asking ourselves. Well, let's draw out a tree diagram, what it would look like. So we don't know what the initial condition is. We don't know how many people are starting here, but that's irrelevant. We just want to know if you do start in A, what's the probability of moving to B after this thing happens twice. So what could happen is there's 2 possibilities. We could start in A, move to B in the first transition, and then stay in B in the second transition. Or we could start in A, we could stay in A during the first transition, and then we could move to B. So ultimately, we're starting in A, and we're ending up in B. These are 2 different situations in which that could happen. So let's look at these different probabilities. Well, for an item to start in A and go to B, starts in A and goes to B, that happens, so let's do this one, that happens 70% of the time. Now, if they're in B and they want to stay in B, that happens 60% of the time. So that is 0.42, or 42% of the time, we would start in A and go to B in this direct path. Now, if we started in A and we want to stay in A right here, that would happen that would happen 30% of the time. And then if we wanted to go from A to B, that would happen 0.7% of the time. So that's 21% of the time. Okay. Now let's just look at the other possibilities. What else could happen? We could start in A, and we could stay in A and stay in A again. Or we could start in A, we could move to B, and then we could come back to A. So these are the only other two possibilities to start in A. If we initially start in A, then these are the only other possibilities. So if we start in A and stay in A, that happens 0.3. And if we start in A, excuse me, then if we're in A again and we stay in A, that happens 30% of the time. And so that is 0.09 or 9% of the time. Now if we started in A and went to B, that would be 70% of the time. But if we went from B to A, that would be 40% of the time. So that would give me 0.28. And if I add these together, I put this plus this together, that gives me 70. This together gives me 30. So the total here is 1, or 100%. Now I can draw this out with a tree diagram like this. We're going to start in A. And now we can move to A or B. So to move to A would be 30%. To move to B would be 70%. Now once we're in A, we can stay in A or move to B. Or if we're in B, we can move to A or stay in B. So if we're in A and we want to stay in A, that would be 0.3. And if we're in A and we want to move to B, that would be 0.7. If we're in B and we want to move to A, we know the probability of that occurring is 40%. And if we're in B and we want to stay in B, that happens 60%. And of course, if we just multiply down here, the only times that we start in A and end in B are going to be here and here. And that's represented by these guys up here. 0.3 times 0.7 is this guy. So here's our 0.21. And 0.7 times 0.6, that gives us our 0.42. So because these can occur at the same time, I can't start in A, go to A, and then to B, and start in A, go to B, and then go to B, both at the same time. We can add these together, and so the total probability, the total possibility of starting in A and going to B after 2 trials is equal to 0.63, which is, there's a 63% chance. Okay. Now watch what happens if I take the matrix T and I multiply it by itself. That's the transition matrix multiplied by itself. Well, let's go ahead, take our transition matrix right here. So I'll go to the matrix, and this is a 2 by 2 matrix, and I'll enter my probabilities. Whoops. Let's go back up here. I want it 0.3, 0.7, 0.4, and 0.6. Okay, now what I'm going to do is exit out. Now watch, if I take that matrix and I multiply it by itself, I want you to see the numbers that I get here. And what I want you to notice, so the resultant is 0.37, 0.63, so let's write that down. 0.37, 0.63, 0.36, 0.64. So what does this tell me? Well, this tells me this is in 2 trials because we used 2 of these guys. In 2 trials, to start in A and end up in B is 0.63, the same number we just got up here. So we can answer these questions, like, for example, what is the probability of starting in A and ending up in A after 3 trials by taking the matrix, multiplying it together 3 times. Now, you might not want to retype it 3 times. So what you can do is you can just go to the matrix, bring it out to the, and then raise it to a power. So if I raise it to the 3rd power, now that tells me after 3 trials. So the probability of starting in A and staying in A is 36%. So only 36% of the time would you start in A and stay in A after 3 trials. Now let's take a look at a little bit more complicated system. So let's say we've got a system that has 3 different states in it. So state A, let me go like this, state A, state B, and C. And I'm just gonna I'm gonna color these so that things going out will be, let's make them blue. So let's say 30% of the people leave from state A to B. 10% leave from B to C. And let's say none leave from C to A. Okay. Now let's do the ones coming in. So let's say from B to A is 20%. Let's say from C to B is, I don't know, 30%. Okay. And let's say from from A, come out of A. Oh, let's see here. I said they're all coming. And I guess it really depends on which way you're looking at these going and coming. So we're leaving A to B, leaving B to C. Okay, coming into A. So let's draw another one coming into A this way. From C. So you think about it as leaving C or coming into A. I guess it's really irrelevant which way you do this. So the coloring, it doesn't matter. Okay, but let's say we put in here, well, we already have 30% leaving, so let's do 20%. So that means that the guys sticking around here in C have to be 50%. If 30% are leaving this way, 20% are leaving this way, 50% have got to stay. Now for B, we've got 20% leaving this way, 10% leaving this way. So for B, we got to have 70% sticking around, because 20%. Okay, now for A, okay, let's say we've got 30% going out this way, nothing going this way. So there's another 70% staying here. So if we did a transition matrix, so here's our transition diagram, transition matrix, we'd have A, B, and C. So this guy's going to be a 3 by 3. And now we got to fill this in. So if you start in A and stay in A, that happens 70% of the time. If you start in A and go to B, that happens 30% of the time. And if you start in A and go to C, that happens 0%. No one ever starts in A and goes to C for some reason. Who knows what they are? Okay, now B to A is 20%, B to B is 70%, and B to C is 10%. Again, if you add the rows, you always get 1. C to A is 20%, C to B is 30%, and C to C is 50%. Now, we might ask the question, what is the probability that someone starts in A and then ends up in C after 3 trials or 3 cycles? Well, to figure that out, we don't want to sit here and write down all the different possibilities, because it can be a lot. Because think about it, we could go, and this isn't even that bad, because there's only 3 states. If you had 30 states or 40 states in your system, you'd be here for a while. So, if you wanted to start in A and end up in C, you could go from A to C. Well, actually, you can't do that, because A never goes directly to C. So I guess that guy's out. Well, let's write it down anyway, even though it has a probability of 0. You could start in A, go to B, and then go to C. You could start in A, and go to C, and then go to C again like that. Okay, I think that might be all the possibilities, because we have to start in A and end in C, and these are the only ways to change the middle. But if we go more than 3 trials, I mean, if we did 5 trials and we had 10 states, you'd be here for a while writing those down. So the shortcut is to figure out how many trials you want, take your calculator, put that transition matrix in here. Okay, so we'll do that. 0.7, 0.30, 0.2, 0.7, 0.1, 0.2, 0.3, and 0.5. Okay, let's just check to make sure those guys look pretty good. Now, if we take that matrix and we raise it to the 3rd power, this new matrix right here that I've got, remember I can use my arrows here to scroll left, right, will tell me the probability of going from A to C directly. So to go from A to C, we start in A, we want to end up in C, that's 0.057, or there's about a 6% chance of that occurring. Okay, so we can use powers of the transition diagrams to go ahead and tell us where we'll end up.